Let's start. Hello, everyone. I am Thomas Marchioro from RAIS ITN, and I'm happy to welcome you to the first webinar organized by RAIS, which is on the topic of understanding metrics in machine learning-based classification. I thought that this would have been a very interesting topic because, machine learning nowadays is very pervasive, not only in the field of computer science, but even in other fields, for example, physics, chemistry, biology, and many others. And so I thought that in particular, learning how to evaluate classification models and how to learn the difference between like the various metrics that are out there is very important. And in particular, the reason why I decided to focus on classification is that there are a lot of metrics which are very interesting, but also they are very hard to understand at first if they're not correctly explained. In particular, they don't have, in my opinion, very intuitive names. So, for example, what is sensitivity? Like, why do I care of having a high sensitivity in my machine learning model? Do I care about having a high sensitivity in my machine learning model? With this webinar, I would like to sort of clarify these questions. And this is a brief outline of the topics that we will be covering today. As I mentioned, I will be covering these main metrics in machine learning classification. And then I will try to focus on what kind of questions are answered by these metrics, and also will try to motivate why do we need to use them. And finally, I would like to highlight some differences between binary and multi-class classification, how you need to handle them differently. So yeah, now let's start with the actual content. Before, I would like to make a brief premise, which is basically the machine learning procedure. Machine learning in general is a very broad topic, and even classification, which is a subtopic, is very broad. Here we focus on the validation and test phases, which is basically we have already trained a rule, a classification model, and we want to assess how good or bad it is, either to train some hyperparameters or to just assess the actual performance of our final model. So let's start by introducing what is binary classification. Binary classification is one of those concepts that are easier to explain with examples rather than with some abstract definition. But the core idea is that we want to find a rule or a model that divides objects into two mutually exclusive classes. For example, we may have voice examples, voice tracks, and we may want to classify whether they belong to healthy or sick individuals. And you see that these are two mutually exclusive possibilities because either you're healthy or sick. Or you may have some images and you want to know whether they belong to a cat, so whether they represent a cat or something else. And finally, the example that we will be focusing today is the example of handwritten signatures. So we have a handwritten signature and we want to determine whether it is authentic or not. So we have seen that we want to evaluate this binary classification rule using some metrics. So let's start by brainstorming some ideas on how to do that. So I think that the first idea that comes to everyone's mind when it comes to evaluate a classification rule is basically okay, we have some test data, and we just apply this rule on the test data, and we check how many predictions are correct, right? So basically, we compute the accuracy as the number of correct predictions over the total number of predictions that we have made. And intuitively, accuracy estimates the probability of predicting the correct class. That is, I give you a random sample, and this is the probability of your prediction being correct. So also another thing is that the more data you have, the more accurate will be your estimation, because if you evaluate your rule on 10 samples is one thing, if you evaluate it on 1 million samples is another thing, right? Okay, great. So let's say, however, whether accuracy is everything that we need. So here I have an example of a rule that has a very high accuracy and was tested on a reasonable number of samples, on 10,000 samples. So if we achieved 90% of accuracy in classifying signatures, so like basically I give you a signature and I classify whether it is authentic or not, and 90% of the times I'm actually correct. So this rule should be somehow good, right? Well, however, the rule that I'm talking about was this. So basically, regardless of the signature that you feed to this rule, it will always return that your signature was authentic. Your signature will always be accepted. So, I mean, I think you can guess that this is not a very good rule, actually. So what's the trick? Well, the trick here is that the data set that we used was simply a data set where 90% of the samples were actually authentic. 90% of the signature were true signatures. Here, of course, I provide just an example with 10 signatures because of space reasons, but you can see that basically the only fake signature was provided by Eve here, and all the others were instead simply authentic. So 90% of the times, our rule that always predicts authentic is actually correct. So the trick consists actually in the way the data are distributed. The test data are, we say that they are imbalanced because 90% of them are in one class, in the authentic class, and the remaining 10% is in the other class. So one important thing is that you always have to check that your test data are representative of the problem that you're trying to solve. And in particular, it is important to check whether there is some class imbalance. Ideally, we would like our test data to be balanced. In a sense, we don't want the distribution of the two classes to be uneven, but ideally we would like to have 50-50, 50% authentic and 50% non-authentic. Okay, now we have seen that one important thing is the distribution of the test data, but we would like also to know whether there is a way to understand if there is some problem in our model just by computing more metrics, like more specific metrics that compute more specific questions. And this will be actually the next part of this webinar, where we will see other metrics and what kind of questions do they answer and when do we need them. So let's see what are these more specific questions actually. So accuracy is a good metric. You should always evaluate it. Actually, it's the first thing that you evaluate, but it's very general, right? Because it just tells you what is the probability of being correct if you give a random sample. But let's say instead that we want to give some condition to this sample. For example, in the case of signatures, we want to say, okay, what is the probability of being correct if we give an authentic signature? So we want to evaluate a series of authentic signatures and see the fraction of them which is correctly evaluated. And we can do also vice versa. So we take all the signatures that are not authentic, and we want to evaluate how many of them are correctly classified as non-authentic. Or we can go the other way around, like we can say, okay, our rule has just predicted that the signature is authentic, but what is the confidence on this prediction? So like, what is the probability that this prediction was actually correct? And now we will see how we can answer to all these questions in a kind of efficient way. Okay, so the first thing that you have to take into account is that there are different ways of being correct or wrong. So in particular, you have your data. Let's go back to the example of signatures, and you can divide it based on the ground truth into positives and negatives. In the case of signatures, the positives are the authentic signatures, and the negatives are the non-authentic signatures. But this is like a division based on the ground truth. You can furtherly divide your data set based on the predictions of your model, right? So you can divide it in like in true positives. True positives are basically the samples which are positives and that are classified as positives. So for example, authentic signatures that are actually classified as authentic. In the same fashion, you can define like the three other metrics. So for example, what are false positives? False positives are actually negative samples that are classified, that are wrongly classified as positives. So like ground truth, negative, prediction, positive. And you can define in the same fashion like false negatives and true negatives. But this is the main idea. And now, okay, we've done this distinction. Let's see how we can use it to answer the questions from before. So let's start with the first question, which was evaluating our model, how likely it is to be correct when the signature is authentic. So in this case, we are in the positive case on the left, and we distinguish between the two cases. So like we want to know how likely we are to get a true positive. Like if we are in the case where we have a positive sample, so we either have a true positive or a false negative. So intuitively, we just need to compute the ratio between the true positives and the sum of true positives and false negatives. And this number is called either recall or sensitivity or true positive rate. It really depends on like what kind of paper you're reading or like in what kind of field you are. But yeah, the definition is this one. And then we have also like the complementary case. The complementary case is when the signature is not authentic. The ground truth is that you have a negative then, and you want to know on those negatives, how many of them are true negatives. So like you want to compute the ratio between true negatives and true negatives plus false positives. And this is called specificity or true negative rate. And actually, you can see that there is some kind of a trade-off between these two metrics, because you know, there are some gray areas where you're not really sure whether a sample is a positive or a negative. And if you decide to get imbalanced towards positives, you are more likely to achieve a high recall. So like, because, you know, if you predict more positives, you are likely to get more true positives, or vice versa. If you have more true negatives, if you evaluate more negatives, you are more likely to get true negatives. So you will have a higher specificity. But now let's see what is the trade-off and when do we want to privilege one metric over the other. So the idea is that, for example, you may want to have a high recall when you have when you're more interested into like recognizing authentic signatures, in a sense that you don't care so much about rejecting fake signatures, but you prefer to be sure of recognizing the authentic one. An idea could be like the fidelity card of a supermarket, because like you may be more interested in not annoying your customers and always accepting authentic signatures, and you could afford to pay the price that sometimes you may have some fake signatures of people who didn't really earn their fidelity card. But on the other hand, if you have a more sensitive task where you're more interested into rejecting fake signatures, then probably you're more interested into a high specificity. That is, you want to be sure that signatures that are not authentic will be always rejected. But of course, you cannot take any of these two metrics as a standalone, because as you can see from this graph, you can easily achieve 100% of specificity and 100% of recall with zero effort. Intuitively, you just always accept or always reject a signature, and you achieve either 100% recall or 100% specificity. And also you can achieve, for example, 50-50, so 50% recall, 50% specificity, just by accepting the signature 50% of the time and rejecting it 50% of the time. I won't go into the details, but if you just do some toy examples, you can easily verify that this is true. Okay, so now let's move to the third question. This was a little bit trickier in my opinion, because you're evaluating basically the correctness of your prediction. So like you have your model is predicting, for example, authentic, and you want to know your confidence about this prediction. And so like this time you're conditioning your samples depending on the prediction of your model. So you are in the portion of the samples where the prediction is authentic, and you distinguish between like the positives and the negatives. So like the ones that are actually authentic and the ones that instead are not authentic. And so this is simply given by this formula, which is true positives over true positives plus false positives. And this measure is what is called precision. Okay, and now we have covered the three metrics that we have introduced before, but actually there is a fourth one. And this other metric is actually derived from the previous metrics, and this is why it is a sort of like bonus metric. So let's say that we are trying to evaluate what is the how likely we are to correctly classify a signature if 50% of the times is authentic and 50% of the times it is not authentic. So basically we are assuming that we have a balanced, some balanced data. So like 50% of the times we will have one class and 50% of the times we will have the other class. And the answer to this question is given by a very nice theorem, which is called the law of total probability. And simply what it states is that this probability of being correct given 50% of the time authentic and 50% of the time not authentic, so 50% of the times positive and 50% of the times you're in the negative case, this is simply given by doing an average 50-50 of the recall and specificity, so of the true positive rate and true negative rate. And this measure is called balanced accuracy. Balanced because intuitively you have like this 50-50 probability of being of the signature being authentic or not. So it's the same as you evaluated the accuracy on a data set which is balanced, which is very good, because it means that actually you can do your evaluation even on data sets which are not like perfectly balanced. So to just give an example, if you have 90% of recall and 70% of specificity, you just do 50% times 0.9 plus 50% times 0.7, and you get that you have 80% of balanced accuracy. And actually, you can do that for any value of p. So in a sense, you can evaluate it for any probability of the signature being authentic or not. So not only 50%, but also, for example, 10% and 90%, or 20% and 80%. So this is a result which is very general and very good. And a positive thing, in my opinion, is that you don't need to do 100 different experiments to evaluate this metric every time with a different distribution, but you can just play with the numbers. Okay, so, and now a final positive aspect is that, we have done this distinction between true positives, true negatives, false positives, and false negatives. And we can use these 4 metrics to evaluate all the other metrics that we mentioned before. So precision, recall, specificity. Accuracy is given by this formula, which is simply intuitively on the numerator we have true positives plus true negatives, which are the cases where we correctly evaluate our signature. And then we have all the possible cases, so the 4 cases that we mentioned. Okay, but the idea is that we all need these 4 numbers, and then we can compute all the metrics that we need. Okay, so let's get back to the rule that we discussed before. You remember it was the rule that always returned that the signature was authentic. And let's see how these metrics are evaluated with respect to this rule. So as before, the accuracy is 90%, of course, because like 90% of the samples are actually classified correctly. The precision is also 90%, and the reason is that, if you remember, the precision evaluates the probability of like your rule being correct, given that the prediction is authentic. And your rule always predicts authentic, and on this data set will be correct 90% of the time. So again, like we need probably to check other metrics to see what's fishy here. And if we see recall, it's actually 100%, because as I mentioned before, in order to achieve 100% recall, you just need to always output positive, because we have that the number of true positives is 9,000 samples, and the number of false negatives is 0. So like 9,000 over 9,000 is just 1. But on the other hand, we have a specificity. So like how many of the negatives are true negatives, so are correctly identified? 0, because our rule never returns non-authentic. So like this is already like an indicator that something very wrong is going on here. And finally, we have the balanced accuracy, which is 0.5, which means that if we give randomly like an authentic or non-authentic signature, our rule will be correct 50% of the time. So, which is basically random guessing, and this is more indicative of the performance of our model. So you see that with the by computing all these metrics, we have now a clearer idea of what's going on with our rule, even if we don't check the distribution of the data set. Okay, good. So now that we have understood how can we use these metrics and why they are useful, I would like to highlight some differences that there are between binary and multi-class classification. So again, let's start by introducing what is multi-class classification. Very straightforward. In binary classification, you had the two options. In multi-class, you have many. So for example, you have, again, a signature, and you want to recognize whether it belongs to Alice, Bob, or Eve. So like you have 3 possible candidates for your signature. Okay, so this time, in order to evaluate the performance of your model, it is a little bit more complicated, because you have to collect the same metrics as before. That is true positives, true negatives, false positives, false negatives, but you have to do it for each class. So like it's like you're doing many binary classifications, and you have to collect these metrics for each of these binary classifications. So for example, you will have that the precision with respect to the class Alice will be the true positive of Alice over true positive of Alice plus false positives of Alice. Okay, up to here seems pretty straightforward. So like we just evaluate all the metrics as before, except for the balanced accuracy. Because as before, like you could compute balanced accuracy using the same idea from before. So you say, okay, I compute the probability of being correct, given that 50% of the times the user is Alice, and 50% of the times the signature is not from Alice. But nonetheless, this is of relative interest. So instead, an idea could be that we want to evaluate, for example, the probability of being correct, given that actually the classes are balanced. So like, what does it mean balanced in this case? We have 3 possible options, Alice, Bob, and Eve. So a balanced dataset would be a dataset where 30% of the signatures, 33% of the signatures are from Alice, 33% are from Bob, and 33% are from Eve, right? So in order to do that, in order to compute the probability of being correct given this specific distribution of the dataset, you just need to evaluate 1/3 times the recall of Alice plus 1/3 the recall of Bob and 1/3 the recall of Eve. So this is just like how you can change the formula to get a more meaningful result. And after you do that, you just like compute all your metrics and put them like nicely on a table as you can see on the slide. And also another nice result is that since both accuracy and balanced accuracy are actually sort of weighted sum of the recalls, you can see that the accuracy and balanced accuracy measure should be bounded by the recall values. That is, that the highest recall should be more than these 2 values, and that the lowest should be instead lower. So this is also like a good way of checking whether your results are consistent or if you have done something wrong in your calculations. So the last metric that we can use to evaluate our model, our rule, is the so-called confusion matrix. And the idea is, as before, we divide the samples according to their class, so like the ones that come from Alice, from Bob, and from Eve. And among those, we distinguish which ones are predicted as coming from Alice, from Bob, and from Eve. And we construct this nice table. And for example, This value represents the number of samples which are produced by ELIS and that are actually predicted as coming from ELIS. This other one is the signatures that are produced by Bob, but they are wrongly classified as coming from ELIS. And you can also normalize this confusion matrix by columns. So basically the idea is that you sum the content of the column and then you divide by each of the numbers by this sum. And what you obtain is the probability of the prediction condition with respect to the ground truth. So for example, this column is the probability of predicting ELIS given that the sample is produced by ELIS, but this other element is the probability of predicting ELIS given that the sample is produced by Bob. Okay, and so we can also give a more visual result by giving more intensity to the elements that are that have higher value. And intuitively, what we would like to have is that the diagonal has the most intense values, because on the diagonal there are the probabilities of predicting the correct classes. Instead, outside the diagonal, there are the wrong predictions. And so this pretty much concludes our presentation. I have some last take-home messages that I would like to leave to you. So remember, always look at the test data when you look at the results, because they could give you some pretty good insights on why you obtain some results. So check if there are like class imbalances, and if the data are actually representative of the problem that you're trying to solve, of the classification that you're trying to make. And second take-home message is like to ask the right questions and get the right answers, which may seem very general, but it's actually very important, because actually the accuracy provides some important information, but it doesn't answer all the questions. And it would be very wrong to just look at the accuracy and just throw away all the other metrics, because you won't have a good idea of how your model works. So always keep in mind these two messages, and this now actually concludes the first webinar. I want to thank you very much for the attention, and if you have any questions, you can either visit our website, raisatn.eu, or just write to my email address. I will be happy to answer or clarify any of your doubts. Thank you very much.